When a massive systemic failure sweeps across an industrial grid, a data center's survival is immediately threatened. Viewing a containerized powertrain unit, or PTU, as a static distribution board ignores the complex logic required to survive a fault. Simply labeling redundant equipment A and B does not guarantee that the load will remain energized. A PTU functions as an indivisible continuity ecosystem. It requires the coordination of electrical distribution, thermal management, and autonomous control logic. That ecosystem relies on strict physical zoning. Power conversion equipment, like switchgear and the uninterruptible power system, or UPS, sit entirely separate from dedicated thermal management, fire protection, and control systems. This is an architectural overview. In the field, all live operations demand approved methods of procedure and rigorous lockout-tagout isolation to protect human life. We routinely hear facilities rated as Tier 3 or Tier 4. Tier 3 dictates that the infrastructure is concurrently maintainable. An operator can safely isolate a single electrical path for planned work without dropping the critical load. Tier 4 adds the mandate of fault tolerance. The system must withstand an unexpected equipment failure or a sudden path interruption with zero operational impact. Look at this standard single-line diagram. Labeling two trains A and B creates the illusion of independence. Overlays expose hidden common mode bridges, a shared chilled water header, a common network switch, or a synchronized firmware update path. A single anomaly in one of those shared nodes can instantly cascade across the divide, taking down the A and B electrical path simultaneously. Redundancy is merely a topology on a piece of paper. True resilience is a dynamically computed state that isolates faults before they can bridge redundant architectures. To maintain that resilience, the PTU must be able to defend itself, even if the facility's central networks go dark. That autonomy operates on a rigid four-layer control hierarchy. At the bedrock, native protection like breakers and fire panels hold absolute authority. Above that sits subsystem control, followed by the local programmable logic controller, or PLC, coordinating the PTU. At the very top sits the central power control and monitoring system, or PCMS. The central PCMS is a request-only supervisor. It processes data and issues governed requests, but strict logical barriers prevent it from overriding the native protection layers below. This hierarchy enforces a critical engineering rule. Command intent is not physical proof. A digital request sent from a dashboard is an electronic wish. Actual proof requires a precise sequence. The local PLC validates the request, mechanical device feedback is received, and the electrical bus is verified actively energized. Assessing that physical reality relies on a strict data contract. Look at this point card. A raw sensor value is useless without its required metadata, a defined name, engineering unit, authoritative source, quality marker, timestamp, and a specific freshness interval. If a communication link drops and that timestamp freezes, the data turns stale. A local logic gate must reject that frozen value, so the system does not execute split-second operational decisions based on outdated information. Operational safety relies on localized, verified physical reality, not on the assumed success of remote digital commands. We can subject this deterministic logic to the ultimate stress test, a sudden, massive loss of the utility grid. At T0, the utility fails, and the automatic transfer switch, or ATS, detects the loss. By T1, the battery ride-through bridges the gap. On this diagram, the lithium-ion battery cabinets supply the UPS DC link to keep the load stable. Inside that brief ride-through window, maintaining the electrical path depends entirely on maintaining the thermal environment. Rapidly discharging a multi-megawatt battery array generates immediate, immense heat. The temperature curve pushes aggressively upward as chemical energy converts to electrical power. The duty and standby precision cooling units must instantly clear this heat. If they fail, the hardware's native protection will trip the system offline to prevent a thermal meltdown. Moving to T2, the standby generator has started, synchronized, and qualified the alternate source. At T3, the ATS executes its transfer. This is a break before make open transition. The ATS physically proves that the bus voltage from the alternate source is stable before committing to close the connection. Finally, at T4, the UPS reconnects to the alternate source and initiates a gradual battery recharge ramp to avoid overloading the generator. Surviving a blackout is an absolute package deal, requiring perfect thermal suppression and deterministic transition logic. What happens when the primary utility grid finally comes back online? The system must never immediately jump back to the first good voltage sample it detects, because a recovering grid is prone to instability. The system demands engineered patience. The returning utility voltage must sit within a strict hysteresis band. The countdown stability timer begins only once the voltage stays strictly within those limits. The retransfer is executed only after absolute source stability is proven. This is followed by a gradual load restoration and the independent generator cooldown sequence. Protecting a load from a recovering grid requires just as much rigid logical discipline as protecting it from a failing one. Maintaining this reliability over years of continuous operation requires servicing high-voltage equipment without dropping the active critical load. To do this safely, we must distinguish our bypass paths. An internal static bypass provides electronic continuity inside the UPS, whereas an external mechanical maintenance bypass routes power around the entire unit. That external bypass creates a verified hazard-free air gap required for technical workers to safely isolate the primary modules. Transferring a live critical load is too dangerous to rely on operator intuition. It requires a hard-coded mechanical key interlock sequence. The system first electronically verifies static bypass to release key A. Key A physically unlocks key B to close the external bypass. Opening the output breaker then releases key C to isolate the modules. If an operator attempts to skip a step, the physical keys refuse to turn in the locks. In mission-critical environments, the immutable laws of physical geometry must supersede digital assumptions to prevent catastrophic human error. That same physical independence applies to life safety. The fire releasing panel owns detection, warning, abort, and discharge entirely on its own. The PCMS is relegated strictly to monitoring these events. It is never permitted to initiate a fire suppression discharge. This autonomy defines the facility's cyber resilience. If the central management network goes dark due to a cyber event, isolated operational technology zones and one-way data conduits lock down. The local PLC continues to run duty and standby cooling cycles autonomously. True operational autonomy means the PTU can protect both itself and the critical load, even when severed from the outside world. Ultimately, Tier 4 labels, redundant architectures, and sleek digital interfaces carry no weight without empirical physical proof. Fault tolerance is a rigorously tested state, validated through an engineering assurance lifecycle. Theoretical design studies advance to factory acceptance testing, and then into site acceptance testing. The climax of that validation is integrated systems testing, or IST. The entire dependency chain is subjected to brutal failure conditions under maximum load, generating hard empirical evidence that matches test cards with verified voltage drop trends and protection trip logs. Transforming a metal box into a trusted Tier 4 asset requires adhering to 6 engineering principles. First, trace the complete continuous power path, including thermal dependencies. Second, assign one definitive local command owner to prevent logic conflicts. Third, always prove the physical state of the equipment. Intent is not proof. Fourth, rigorously separate A and B dependencies physically and logically. Fifth, test the entire system under actual physical stress. And sixth, govern the configuration lifecycle strictly from day one. Operational readiness is dictated by the laws of physics and recorded empirical evidence, ensuring the PTU stands as an observable and demonstrably resilient component of the data center's power infrastructure.